Biology, and welcome to a quick video going over accuracy, precision, types of computations you can do on your summative and looking at some data. So a quick reminder when we talk about accuracy and precision, accuracy is whether or not a data set is hitting a known target or a value that we have in mind, and this is often useful when we have a known entity or we're comparing identical treatments to one another. So two different experiments where you ran for 60 seconds. Now, precision is in reference to a collection of data points that are all similar to one another. So if we look at these green diamonds, they're all really close to each other. It would be likely that I would expect a 6th, 7th, 8th, or 9th green diamond to appear in this space. So what does inaccurate but precise data look like? Well, the data set has a small range and a small standard deviation. Its trend is predictable or is consistently changing in a way that makes sense. And when we think about the inaccuracy, it's very far from the average or the target, which is this green circle here. And if we compare two identical treatments or 5 dart throws, they're very different from each other, but they have similar ranges or standard deviations. Now, when we talk about accurate but imprecise data, as we can see with these black diamonds, the data is all over the place. There's a large range, there's a large standard deviation. It generally looks pretty inconsistent and appears a bit random. But when we average the X and Y values of up and down, left and right for these 5 diamonds, they hit the target. And we can see that also here with these 5 blue diamonds, when we sort of average out where these 5 blue diamonds are in terms of left and right, up and down, it'd likely be right here as well. Now the dream is accurate and precise data. The data has a small range, it's consistent, the average is being hit, and when we do it again, we get very similar results. This pink version might be slightly less accurate, but they're basically mirror images of each other. Now, inaccurate and imprecise data is basically garbage. We could call it random nonsense, doesn't make a lot of sense. It generally looks like this. Huge range in standard deviation, inconsistent, unpredictable patterns, average is not being hit, and if we do this again, we would get another sort of scattered 5-set piece of data set. Now, things that we can do for manipulations, I'm not sure my animations are going to go quite well, but I'll talk about it. One way we can increase accuracy is by increasing the target size. So if the green is the target, making this green circle would increase the accuracy of our data, or what we think is accurate. For example, I might say my data is accurate if I'm 3 plus or minus 1. But then if I make my data 3 plus or minus 3, well, more data can fit in that range. It might appear more accurate even though I'm sacrificing some level of precision. Second thing we can do is increase precision for the data by just adding more increments of data measurement. So for example, I had an orange, a blue, and a green. If I had 5, 6, 7 different circles in this dartboard, I might be able to have a more precise set of data by saying this happens to be a 2, but this is a 3 because it's slightly closer to the average. So let's talk about range and standard deviation, which are 2 of the values that you're computing in your data set. Now, range is just going to be your smallest and your biggest number subtracted from each other. Now, the standard deviation, however, is a statistical computation or calculation, and it sort of determines the variance of data. And when we talk about variance, we're really talking about how far is an individual data point from the average, and how does that compare with the rest of the data and its variances. These 2 data sets show an average, which are in this green line here. The prefix mu in math means average, and omega, which is right here, is often used for standard deviation. This data has a much smaller standard deviation, which means more of the data, about 34.1%, or a third of the data, is clustered in a much smaller range. Generally, a standard deviation is used to talk about the distribution of data, we say plus or minus 1 standard deviation from the mean is about 70% of the data. 2 standard deviations is about 95, 96% of the data. So having a smaller standard deviation often means most of your data is closer to the average, which implies both accuracy and sometimes precision. So when we talk about computations, 2 things that you can do in your Google Docs is take your standard deviation and divide it by your average. So for example, if I have 2 standard deviations of 0.3 and 0.3, but my average is 3 versus 1, this data set of 3 plus or minus 0.3 is way more precise than plus 0.3 and 1. And that's because 0.3 is significantly larger in relationship to 1 than 0.3 is to 3. This is 30% of our value. This is 10%. So a smaller standard deviation compared to a larger average is always going to be better for precision and also accuracy. Now, if your standard deviation is small, but your range is really large, this often means that your data has some large outliers, some imprecise measurements, some things that didn't maybe make sense. So for example, for the same standard deviation of 0.3 and 0.3, this value of a range of 1 would be a lot better. This means my data is really tight. It's quite accurate. It might be accurate. I'd have to look at the average, but it's very precise. But 0.3 and 0.5 would be even better because this is saying that the range and the standard deviation are effectively the same. That would be the difference between this and this model. So in a nutshell, we can look at standard deviation and range and also trends in data to have a really good sense about how our data is going. So let's take a look at a spreadsheet. This is a group that had me actually physically ski for 30, 60, and 90 seconds on the indoor machine. So I'm going to look right now at run 1 for 30 seconds and run 4 for 30 seconds. One thing I need to do right now is do equals average to make sure that I'm getting all the right data. And notice there's this negative 17.6 right here. If you have a negative number for total length, you just want to delete it. Perfect. So if I'm looking here, my average is 2.54 seconds. My standard deviation is 0.25. That's not too bad because it's about a tenth of my average. So 0.25 divided by 2.5 is about 0.1. Not too bad. And my range is 0.93, so about 4 times larger than my standard deviation. Let's take a look at run 4. If I go here, I'm going to delete this. 2.275. So if I'm thinking about this value and this value, let's come here, Command copy, Command paste. We need to paste values only. Nice. My 2 averages are actually pretty close to each other. On average, my breath rate was 2.3 seconds and 2.5 seconds. That's really not that different. My standard deviations, though, are a little bit different. This is a bit bigger, quite a bit bigger than my first standard deviation, so it might be a little less precise. And notice my range is twice as big. So it looks like on my first trial, my data is showing some good level of accuracy. I'm getting 2 treatments of 30 seconds that are both pretty similar, but I see one set of data with some precision and one set of data with imprecise data. So that's one thing that you can do when you start to look at your data. And the same thing is true for flow out and flow in terms of how much you are breathing out and in. One thing to note is make sure your data is all formatted correctly. So notice if I look here, negative 76, that's because this group had a 0.534 written as a 534. I'm going to go there and make that change there. That, I think, is a little bit better. The only other thing that you can do, which I think might be important, is thinking about graphing your data. And here is why. Again, I'm going to highlight this breath data. I'm going to highlight this data so I can look at how my breath length changes. I'm going to go to Insert, Chart. Let's see what I get. Okay. Breath is x-axis, length is series. That looks great. I'm going to go here and do a line chart. What I'm noticing is over time, it would appear that my breath length is getting longer. Now, you might see that and say, oh, it's a really, I'm actually going to make this a scatter plot, and I'll tell you why in a second. You might look at this and say, oh, this data sucks. This is garbage. Every breath is different from the other. Well, if we're assuming that breathing is related to a negative feedback loop, my breath rate should get longer and longer as my body regulates more and more towards homeostasis, getting away from the stimulus, which was skiing. So if I go here and go to Customize, Series, and do a trend line and add an R-squared, boom, 77. That's a really good R-squared value. That's telling me that my data actually looks pretty predictable. It's likely that I could predict with some level of accuracy how long breath 7 would be. And if I make this trend, say, logarithmic, doesn't look as good, not that much better. It looks like, indeed, it is pretty predictable by just assuming my breath would get longer and longer as I moved further and further away from exercise. Making these graphs can also be really useful. If you need help with them, feel free to ask. So the last thing to do is look at our homeostasis summative. I'm not going to go over the questions now, but I do think that you might want to start making tables where you can put in values of average, standard deviation, range, your standard deviation divided by your range, and your standard deviation divided by your average, and also making any graphs of your data. I realize many groups are still not finished fully putting in their data, but this is the first step to being able to answer questions 1, 2, and 3. There's not a lot of official homework. I think what you want to be doing, depending on the class that you're in, is making sure that your notes are up to date with what types of different data looks like, what you understand standard deviation and range to be, and the sorts of things that you can be doing with your data set. Each of you is responsible for organizing and generating graphs and tables for your lab on your own. This is not a group activity. And there will be assessments that are in class at points throughout the next semester where I ask you to do this on your own. So this would be a great first step for practicing. I hope this has been helpful. Reach out to me with questions or emails, and I will see you next week. Bye for now.